think your question, Justin, is, what is it about the function itself that allows for a gap in the domain to be a removable discontinuity instead of a vertical asymptote? Like, why does one result in a hole and one result in the spikes? We'll get to that. We'll get to that. That's a very deep question. Yes. Yeah.
Why is it when you simplify a rational function, it's not equal to the original equation?
Why is it that when you simplify a rational function, it's not identical to what you started with? That's a good question. Other cool questions. I know other ones. Supposed to come up with 2 each. Any other questions? Any other questions? Nothing? Really? Okay, yeah, Maxie.
The factoring for powers higher than 3, does
Yep.
it still work, like if you get up until the 5th power?
Okay, so is the method we're going to learn to attack cubics going to work with quartics, quintics, and higher? Right? That's what you're asking? Yeah.
Why does
Why does synthetic?
Synthetic.
Yep.
Synthetic division can work, and why it makes sense?
Okay. Let's do the initial questions here. Let's do the initial questions. So, first, what's the point of removable discontinuities? The point is some functions have them, some do not. They result in very different behaviors than vertical asymptotes. They result functionally algebraically from very similar constructs, but how the function behaves around them is radically different. A removable discontinuity is literally just a hole in the function.
So if there's a removable discontinuity, there's no vertical.
Exactly. You either have one or the other. You cannot have both. You get spiky craziness around vertical asymptotes, and you get a nice, neat, just dot, a hole. Can you see those holes on your calculator? Generally not, unless you zoom in really, 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 really far, and the resolution can actually take it. Does your calculator actually graph open dots? No, it doesn't. What? You can't have both at one x value. There could be a removable discontinuity over there and a vertical asymptote over there, but they can't be at the same place. You can't have both of them at the same x value. Like at x equals 2, you could have a vertical asymptote or a removable discontinuity, or the function could be just fine. You can't have both. One preclude the others. Yeah.
Probably, if they are at the same time, it means the
can't have them.
Have already include.
No, you can't have them at the same time. They're mutually exclusive. One of them is an open dot, and one of them is going like this. You can't have an open dot at this. What is it about a function itself that allows for a gap in the domain to be a removable discontinuity and not a vertical asymptote? The way you can think about it is the exact same thing is happening in the numerator as is happening in the denominator around that x value. Certain things are going to happen around the x value to cause the function to spike infinitely up. Certain things are going to happen around the x value to spike infinitely down. That results in a vertical asymptote. But if exactly the same thing happens on the top and the bottom, if super craziness happens in the numerator and the exact same super craziness happens in the denominator, what happens to the super crazinesses? They cancel out. They turn into 1. If you have the same thing over the same thing, it's 1. So you can think of it as the overall behavior is crazy up here and crazy up here around that x value. But what happens when you have crazy over crazy? Too bad that doesn't work out in real life, huh? 2 crazy people equals a normal person? Wow, we'd have a really sane country. Okay, why is it that when you simplify a rational function, it's not identical to what you start with? Because when you cancel something out of the top, the numerator and denominator, You are eliminating something. You are taking something away. In the past, this hasn't mattered, because the depth in the past, the depth with which we've examined functions, we haven't gone very far. Did it matter if one specific value was gone? Not really, no. Is the method we're going to learn to attack cubics going to work with quartics, quintics, and higher degree polynomial? Yep. That's the whole point. I'm giving you a way to attack any polynomial. Does this method always work? No. But it's the first method you're going to get that allows you to attack any polynomial. Right now, you have quadratics. What's your fail-safe with quadratics? Quadratic equation, but that only works with quadratics. Is there a cubic formula? Side questions here. So, that's a good question. I like that. Is there a cubic formula? What do you think? Yep. Is there a quartic formula?
Yep. Yep.
Yep. Is there a quintic? That means fifth degree? What do you think? Nope. It's a really, really interesting fact of math. There is a cubic formula. You plug in A, B, C, and D, and you get out the three answers. Two of them could be imaginary. There's different kinds of sets of answers. Quartic, yeah, same thing. A, B, C, D, and E. Quintic, you would think you could just arbitrarily do it, right? Now here's the thing. Why isn't there a quintic formula? What might you think is the reason?
Too much.
Well, for example, we don't have a perfect energy source, people assume, because we haven't found it yet. So there is no quintic formula because,
Not found it yet.
guess what? People have proven there is not one. People have proven that one doesn't exist in multiple different ways. There is no formula for finding the roots of a quintic directly. Isn't that cool? So here's a little bonus homework if you want this. Bring in the cubic formula. Just bring it in. Write it down. And second, how about this? Bring in the quartic. You look it up. Just take a look. Okay, why does synthetic division work? What the heck? Yeah, that's what we're going to practice. Sound fun? Okay, let's pause. Let's talk about R4. So you did the first three steps, right? That's what you're supposed to do?
Mm-hmm.
Let's check this out.
What is this program?
One note.
How spell it?
One note. So if you want to examine this in terms of DIS, domain, intercepts, and symmetry, if you want to go for domain, if you want to go for intercepts, and you want to go for symmetry, what are you going to have to do to both the top and the bottom at some point in this process? Factor. Can someone tell me what the factorization of the numerator is? Can someone tell me what the factorization of the numerator is? 3x plus 1, yep.
And
2x minus 3, yep. Over, can someone tell me what the factor form of the denominator is? 2x minus 3 times what? X minus 2. When you're in fully factored form, that is super, super helpful because it helps you figure out the domain immediately. Can someone tell me what the domain of this function is? Said properly? Olivia. Or 3/2. Yep, that is absolutely correct. The things that make the denominator 0. Can someone tell me what the... Now, looking at the original function, that's the easier way to do this. What's the y-intercept of this? What's the y-intercept? When x is 0, what's y? Can someone raise their hand and tell me what it is? What is it? Nope, close. Negative 1/2. Yep. Now, you get to have more fun. What's the x-intercept? How many are there? Are there 2? Okay, so we think the 2 are when the numerator becomes 0, so that's at what? Negative 1/3, 0, and where else?
3/2.
3/2, 0. Can you notice something? There's a slight contradiction here, everybody. There's just one what? Yes, because look at the domain, everybody. X can't be 3/2, so this right here not an intercept. What's going on there? Let's continue on this to VARD. Let's just jump ahead a little bit. We'll skip over. We can skip over symmetry and we did the domain intercepts. Well, we can say symmetry. Did anybody have any conclusions about symmetry on this?
Neither.
Neither. It is neither. So again, VARD, vertical asymptotes. You have to fully simplify to find the vertical asymptotes. You have to in order to fully simplify this, you need to factor. What cancels?
2x minus.
So can someone tell me what is the only vertical asymptote?
2.
A vertical asymptote is a line. It is a vertical line.
Equals
When I ask you what a vertical asymptote, where a vertical asymptote is, or what is the vertical asymptote, you would need to say, to answer this question, x equals 2. You would have to say x equals 2. You can't say 2. 2, not a line. What about removable discontinuities? That's what you canceled out. We know where it happens. What x value does it occur at? The removable discontinuity it's an open space, and it occurs where in the x value that got canceled out. What x value got canceled out of the domain here? 3/2. So we know the removable discontinuity occurs at 3/2, but can you plug 3/2 into the original equation? No, because it's not part of the domain. What happens if you plug 3/2 into the original equation? Error. Divide by 0 error. But if you take the simplified form of this equation, what is the simplified form? 3x plus 1 over what? Over x minus 2. If this is this, you can think of this as R3 simplified. Can we plug it into there? Yeah. So what is R3 simplified of 3 over 2? That's going to be 3 times 3 over 2 plus 1 all over 3 over 2 minus 2. Fractions! 9 over 2 plus 1 over what? Negative what? 1/2. That's going to be 11 over 2 times negative 2 over 1. So it turns into 2 over 2, which is... So where does the removable discontinuity occurs where?
3/2, negative 11.
3/2, comma, negative 11. Meaning, this graph is going along nice and dandy, and whenever it hits the x value, x equals 3 over 2, there's an open dot right there, and what is the coordinate for that open dot? 3/2, comma, negative 11. Are there any weird spikes around it? No. There's just an open dot. There's just an open dot. There's an open dot right here.
Why did we plug in 3/2?
We plugged in 3/2 because we want to know where the removable discontinuity occurs. We cannot plug the 3/2 into the original equation because 3/2 is not part of the domain. So we plugged it into the simplified form. The only difference, can someone tell me what is the only difference between the simplified form and the original form? We canceled out the same thing, but structurally, if I graph both of them, they'll look identical except for one point. What point is that? The removable discontinuity. This one right here is the same as the original except for what? Except what? The RD is what? Filled in. By canceling out the top and the bottom, by canceling out the 2x minus 3, that removable discontinuity, can you now evaluate it at 3 over 2? Yeah, you've taken that hole and you've plugged it in. It's the exact same thing. Here's a really simple version of what I'm talking about. Has everybody graphed this before? This is where you all say yes. There's no trick here. This is just a line. Looks like that, right? What happens if I did this? This looks crazy, right? I mean, that's not y equals x. If you graph this function right here, what will it look like? What did I multiply it by, everybody?
1.
1. So, when you multiply by 1, you know this. Pull it out. Come on. What happens when you multiply a function by 1?
Same.
Stays the same. This function will look exactly the same as y equals x, except for what?
Except
There will be a removable discontinuity at negative 2. So at negative 2, right here, negative 2, there will be a open dot, and a removable discontinuity. The only difference, if you take this function right here and graph it, it will look exactly like y equals x except for one thing. What's that one thing? Removable discontinuity. Think about it this way. This function, x plus 2 over x plus 2, when you plug in, what's the domain of that function?
X cannot be equal to
Any number you plug in except for negative 2, what does that function equal?
x equals any numbers except
Plug in pi. What's pi plus 2 over pi plus 2?
1.
It's not a trick question. What's 10 plus 2 over 10 plus 2? 1. So we are, for every single case, multiplying x by 1, except for you can't plug in negative 2. So by multiplying by x plus 2 over x plus 2, nothing changes except all of a sudden you can't plug in negative 2. That's it. So you can think of this right here, this original function is exactly the same as this, except we've tacked on, what have we tacked on? We've tacked on 2x minus 3 over 2x minus 3. Does that change anything? Not really. It just adds a small dot where? 3 halves, comma, negative 11. So if you cancel it out, it doesn't do anything, except there's an open dot there. So could you, if I asked you for this, let's say I asked you this. Let's say I gave you this function right here. And I'm telling you the blue function is y equals x. And I'm going to tell you that, I'll use a small eraser here. There's a hole at negative 2, negative 2, negative 5, and a hole at 3, 3. Can someone tell me just off the top of their head what this function is? Y equals? Denise, yeah?
X
Denise, yeah? Yep. If you multiplied this out, what type of function is this?
quartic.
What's the kind of function we're looking at? Rational function. Thank you. Woohoo! We have a winner. If you multiplied this whole thing out, it would be a rational function. Would it look much like y equals x? No. The top would be a quartic, right? 4th degree. And the bottom would be a cubic. Could you, being you precalculus students, could you multiply these out if you wanted to? Sure. Would it take you a little while? Would it be really easy to make a mistake? Yeah. Could you multiply these out? Assuming you multiplied them out, it's decently challenging. What's much harder? Going backwards. Let's say I multiplied that out and just gave it to you and said graph it. You guys would be like, no, I can't do that. Right? But if you factored it out, everything canceled out, and all of a sudden you'd end up with y equals x with 3 open dots. Do removable discontinuities make a little bit more sense now? Yeah. But what's the key? Can I just ask you this? What's the key to this whole process? If I gave you some rational function to begin with, you're going to learn about domain, intercepts, symmetry, vertical asymptotes, removable discontinuities, horizontal asymptotes, oblique asymptotes, stuff like that. Or that's coming, right? But what's the key to it all? You have to be able to simplify, and what's the key to simplifying? Factoring. If you can't factor this whole process, you go nowhere. There's this huge thing, and the key in the middle is factoring. I love factoring, and so will you. That's right. I love factoring, and so will you. But you like those videos with the pretty pictures, huh? So here's what we're going to talk about.
Can we have the copy of it?
It's online. I can send out the links. Synthetic division. So you've seen it so far. You've seen it in practice. We're going to spend some time on this. And here's what it essentially does. Can you remember what does synthetic division do? It only does one thing, really.
Factor the.
It helps you factor, but what is that last number? The coefficients are in there. Synthetic division evaluates
Irrational number.
evaluates polynomials.
Yeah.
Let's come up with a simple one. Let's come up with a simple cubic. Let's say we had f of x is equal to, let's make something so it doesn't get too big. How about x cubed minus 2x squared plus x plus 3. If you wanted to attempt to factor that, it
costs a lot of work.
You are looking for zeros. Why are you looking for zeros if you're trying to factor that polynomial? Well, let's look at a simple one. How about g of x is equal to x squared plus 5x plus 6? If I wanted to find the zeros of that polynomial, we know that that's equal to x plus 2 times x plus 3. That's a quadratic, and it roughly looks like this. Here's 2, here's 3. I'm not doing it to scale, but it looks like that. It looks like, sorry. It looks roughly like, I'll do it together. There's 2, there's 3. Here's your parabola. Looks roughly like that. Well, again, what were the zeros of the polynomial? 2, 0, and 3, 0. Correct? What were the factors? So these are zeros. These are factors. So if 2, 0 was a 0, if 2 was a 0, what has to be a factor? 2. Not 2 is no, 2 is not the factor. 2 is the 0. Here's the 0, everybody. What's the factor that corresponds to that? Oh, and I graphed this wrong, didn't I? Why didn't you correct me here, kids? Come on, I make mistakes all the time. Help me out. Oh, throw me a bone. So let's say that this is -2 and -3. Thank you. So we have our parabola crossing at -3 and -2. Sorry about that. So if -2 is a 0, what has to be the factor? X plus 2. If -3 is the 0, x plus 3 has to be a factor. And if you know each is a factor, you know both of them multiplied together create the polynomial. We're good so far? So let's go back and look at our, I'll pick a different one actually. Let's pick one, let's pick something that we're going to actually look at, you're going to look at tonight. So let's look at this one. Our goal is to graph that by hand. We want to find out about the domain, what else? Intercepts, symmetry, vertical asymptotes, and removable discontinuities. The key to it all, so far, we need to be able to simplify, which we do by... So we're really interested in, let's try to factor one of these. Which one do you think is easier to factor, the bottom or the top? Let's try the bottom. Let's focus on the denominator for a second. So if you look at this, x cubed minus 4x squared plus x plus 6, this is a cubic, correct? So theoretically, if it's factorable nicely, is it guaranteed to be factorable nicely? No. If it's factorable nicely, it'll be x, x, and we know it's 3x's because what's the coefficient right there? 1. Well, here's the thing. These are each factor. This is the first factor. We'll call it factor 1, factor 2, factor 3. Each factor has a corresponding what? For every factor, there's a 0. So this will be called that one R. Let's call that R1, R2, and R3. So what if this is the factor right here? What's the 0? Yes, the 0 is R1, R2, and R3. And what are zeros? Zeros are numbers that what? Where the graph crosses the x-axis, meaning when you plug it into the original equation, what do you get out? You get out 0. So we're interested in finding numbers that when you plug them into a polynomial, you get out 0. So if we look at this, let's look at this. What are we? We're starting with x cubed minus 4x. We're starting with it right here. Do we have any idea where to start? We could just start throwing numbers at it, right? And would it be nice if we just found a number that when you plug it in, it equals 0? Let's say when we plugged in 5, it equaled 0. What does that tell you? What's a factor? Minus 5. If we plugged in 5 and the whole thing evaluated to 0, you would know that x minus 5 is a factor. Is that helpful? Very helpful, especially since if you can make if you take one factor out of a cubic, what are you left with? Quadratic. And are you home free when you get to quadratics? Yes. Your goal is to stumble bleeding and scratched and beaten up into quadratic land. That's safe for you. That's your goal. You need a list. You need something to start with. I gave you that list. I told you in the video last night. Now, I know it takes a long time. I gave you way too much information last night. I apologize for that. I'm going to try to break it down further. I'm trying to get a balance here. It was called something with a P.
Potential rational zeros.
Is a polynomial guaranteed? Is it zero? Is it OES?
Zero.
Is it like that? No, it's just see. I got it right. Okay. I doubt myself sometimes. Is a polynomial guaranteed to have any rational zeros? No. But if it does, you have a way of listing all the potential ones. So here they are. you look at, what are the two numbers you need to look at? Someone raise their hand. What's the first number we need to look at? Macy. We need to look at 1 because it's the leading coefficient, and we also need to look at 6. You take all the factors of 6, which are plus or minus 1, 6, and is 1 your favorite number in the world for a leading coefficient? Yeah, because if that was anything other than 1, you'd have twice as many potential rational zeros.
Wait,
So now, those aren't the potential rational zeros. You pair them all up here. So you make 1 over 1, 2 over 1, 3 over 1, 6 over 1. Is 1 a really nice denominator? So what is the list of potential rational zeros? 1, 2, 3, and 6. But not just positive, also the... So how many total do we have? 8. We have 8. That seems like a lot, right? Is that a lot better than not having any idea where to start? That's great. Overall, 8 is going to be a great number for you to work with, considering... Let's say, what happens if, I just have a question for you. What happened if instead of 6 that was 32, and if instead of that, that was, I don't know, 4? How many factors of 32 are there? 1, 2, 4, 8, 16, 32, 1, 2, 4. And then you have to pair them all up. Is there overlap sometimes? There is, but is that list going to be bigger? We have 8. That should make you happy because now we have 8 numbers to test. I gave you a hint last night. Where do you start? Which numbers do you start with? Small, positive. Each potential rational zero has an equal chance of being a 0. So start with the easiest ones to test. Are you ever going to test all of these? No, because once you find 1, you can factor. You can start factoring. Once you find 1, you can start factoring. You don't just test all of these. What do you set up? What was the key to this setup here? So I'll write this down. We have x cubed minus 4x squared plus x plus 6. What do you have to write down?
1, 4, 1, 6.
Negative 4, 1, and 6. And then you make this nice little line, and you pick the number you're going to test. What do we want to start with?
1.
Always start with 1, okay? Always start with 1. That's your testing this number. And the number you end up with, what number do you end up with right there? That's the polynomial evaluated at 1. You drop down the leading coefficient, and what do you do now? You multiply. Multiply by 1, and you get? You add, and you get? Multiply by 1, and you get? Add, and you get? What this is saying, if this is f of x, we just found out that f of 1 is 4. We just found out f of 1 is 4. So therefore, x minus 1 is not a factor. Do you erase this? Please don't. You need to keep track of the zeros you're testing. So we just tested 1. Did 1 work? No. You might be able to get a test, maybe try negative. It doesn't seem like it. Let's skip to, what do you want to test? Let's try 2. You'll develop intuition about this. So 2, do you have the same coefficients? Yep. So now we have 1, 2, negative 2, negative 4, negative 3, negative 6, and? So now we know that f of 2 is equal to?
0.
So, therefore, that's what those 3 dots means.
X minus 2
is a. But the really cool thing is, everybody, what awesome thing about synthetic division? You now know that x minus 2 times something is equal to the polynomial. The problem is, you don't know what that is. Or do you? You do. It's right there. You see these coefficients, right? You see these numbers? You start with, this is the constant, this is the x, and this is the, they go right here, and it turns into 1x squared minus, are we home free? We now have x minus 2. Does that factor? X minus 3 times x. So negative 1 did work. We could have done that. But is that the fully factored form?
Yeah.
After we factor the numerator, we need to factor the... And then can you do all 5 steps? You sure can. You absolutely can. The key to this is patience and be careful. We're going to get back to your really good question, Justin, which is why does this work? Why does it give us the coefficients? Just to give you a preview. Just to give you a preview of what's to come. Right now we're doing synthetic division. SD.
I know it's synthetic.
We need to learn how to do that. We're eventually the last step. We have step 6, 6 and 7 depends on how I break it up. Something called. Anybody know what that stands for? Rock and roll.
Long thing.
Yeah, so tonight everybody, homework. Ready? Find the cubic. I'm going to make it mandatory. Find the cubic. 2, is it R4, what are they? R5 and R6?
R5 and R6.
You're going to run this VARD on R5 and R6. And then the third thing is watch rational functions part 3. I'll try to make it shorter, everybody. Have a good day.